So welcome everyone. It is Saturday, October 1st, the first day of October, and a wonderful busy month we have ahead of us, I'm sure. I'm really excited to have our guest speaker, Marcin Sawicki, with us today. I've been looking forward to this. And it's too bad that the rest of you weren't privy to his emails, because I'm sure you'll hear the excitement in his voice when we actually hear him talk. But I know from his emails that he was equally as excited. So it'll be thrilling to hear him talk about the NEAREST project and his involvement in it as a Canadian. Yay! I'm going to share my screen for a moment. Again, welcome. If you want to reach our Halifax Centre, you can go to our website at halifax.rasc.ca. We have a YouTube channel at RASC Halifax. And if you have any questions at all about the Centre or any aspect of astronomy, please email me at president@halifax.rasc.ca. Our agenda today, and I'm sorry, but I could not resist that picture of the pumpkin when I found it. Welcome and acknowledgements. The acknowledgements I'll go through in a moment. The photo montage. David Hoskin had a family emergency, so he was unable to attend today's meeting. So in his place, we have Jerry doing his photo montage that David actually did put together for him. Our special guests are Dr. Marcin Sawicki to address NEAREST, Webb's Made in Canada near-infrared imager and slitless spectrograph. And our very own Chris Young will give us another edition of the sky lore and tell us some really fascinating stories about the skies and the stars from other cultures. And again, because David is absent, Lisa Ann Fanning offered to do the What's Up in the October Skies for us, so thank you. And then last but not least will be the news from the board. And I promise this time, I won't just close the meeting. We actually will have an Astro Chat, unlike we had in September where I canceled it for some strange reason. So that is our agenda for today. I would like to make acknowledgement of that we are in Mi'kma'ki, the ancestral and unceded territory of the Mi'kmaq people. This territory is covered by the treaties of peace and friendship, which Mi'kmaq and Maliseet peoples first signed with the British Crown in 1725. The treaties did not deal with surrender of lands and resources, but in fact recognized Mi'kmaq and Maliseet title and established the rules for what was to be an ongoing relationship between nations. The other thing I would like to acknowledge is our inclusivity and diversity statement, which reads, the RASC and the RASC Halifax Centre believe in and practice inclusivity and diversity. All are welcomed regardless of age, disability, gender reassignment, marriage and civil partnership, pregnancy and maternity, race, ethnic origin, color, nationality, national origin, religion or belief, or sex and sexual orientation. We are opposed to all forms of unlawful and unfair discrimination. And I'm going to introduce our very first guest. And for that, I'm going to read what he sent me in part. Quite an accomplished gentleman. He looks so young to be so accomplished. He's a professor of astronomy and physics. He's a Canada Research Chair and Director of the Institute of Computational Astrophysics at St. Mary's University. He studies how galaxies first formed when the universe was just a few seconds old, or a percentage of its present age, and how they subsequently grew over time to become beautiful giant structures such as our own Milky Way. He obtained his BSc at McMaster and his master's and PhD at U of Toronto. He held appointments at the California Institute of Technology, the National Research Council of Canada, and the University of California at Santa Barbara before coming to Halifax. He has served on advisory panels for NASA, the National Science Foundation, and major international astronomical observatories. And for nearly 2 decades, as I said, he looks too young. Professor Sawicki has been a core member of the science team for NEAREST, the Made in Canada instrument on the Webb telescope, and he's now excited beyond belief, his own words, to be using the Webb to further his scientific endeavors. So welcome, Marcin, and we're really looking forward to this presentation of yours.
Well, I'm really looking forward to, actually, well, not just looking forward to, I'm really excited to be here. It's been a long time since I spoke to this group. Just checking my notes, my calendars, and it's been 15 years that I gave a talk at the Halifax to the Halifax Rascals. So really happy to be back, and yeah. So why don't we get started? I have some slides so that I can have some pictures for you to show. let's see if I can figure out how to do it so that I can see my slides and my and my notes. So just be patient with me. First of all, can everybody hear me? I guess that's the most important question.
Yes.
Okay, great. So let's see. And so you can see that. And let me start my presentation. And can you see anything or no?
Yes, we can. You can see Nearest.
Oh, awesome. Got it on the very first try. Okay, so I'm going to tell you about Nearest and what the heck it is and why the heck do we have it. And so if I can advance my slides, good. I'll be looking off to my main screen because I am. So if I'm not looking at you, that's because I'm looking at where my slides actually are. I like this picture. I have a copy of this as a poster on my wall, and right, it's a famous Paul Gauguin painting, which it lives currently in Boston, but he painted it in Tahiti, I believe. And up here in the corner, I don't know if you can you see my mouse, my cursor? Okay, up here in the corner, he says in French, and I'll just translate into English: where do we come from? What are we? And where are we going? So some very, very philosophical questions that many of us have asked ourselves at one point or another in our lives, not every day, but once in a while, right? And that's something that motivates me as well. And I can't really say very much about what are we. Right? Maybe that's a question for philosophers or possibly biologists and anthropologists, religious scholars, and so forth. Where are we going? Well, who knows? But where do we come from? Well, that's something that I think as a scientist I can help address. So there it is in orange. Where do we come from? Right, the big fundamental question. And the way we can, as astronomers, the way we can tackle this question or shed some light on it is by studying the distant universe, because our origins ultimately lie in the stars. You are all astronomers. I don't need to tell you this, but I will, or just to set the stage. We're all made from stardust, and that stardust that we're made from has not been made in our star, in the sun. It's been made in previous generations of stars that no longer exist, but did exist in the past. So our story, where do we come from, really has to go back into the early times in the universe. And as astronomers, we go and travel back in time using time machines. And our time machines are the telescope. So here's Edwin Hubble observing the distant universe. And what we do as astronomers is we observe slices of the universe at different distances. The farther the farther a slice is, the longer it took information from that slice to get to us. And therefore, we see the universe as it was way, way, way back in the past. Right? And if you have several of these slices, you can construct a time sequence that tells you about how the universe and its contents have evolved. Right. So two concepts here fundamentally. One is redshift, how far a galaxy is from us, and therefore how long it took its light to get to us is related to its redshift. That's an observable quantity that we can measure, the redshift. And it's also related to look back time. So we can convert between redshift and look back time. Look back time basically means how long back in time you're looking when you're looking at a certain redshift. Right, so we can look back in time. When we look at the moon, it's only a second and a bit away back in time, because that's how long it took its light to get to us. When we look at the closest star outside of our solar system, that's 4 years of look back time, and distant galaxies can be millions or even billions of years away in look back time. Well, what we want to do then is to look back in time as far as we can. And so our time machines are, well, in the 1990s, it's ground-based telescopes. And then Hubble came along, and then we could reach further and further back in time. And here's the scale of how far away in redshift we could reach. So we could push to about redshifts 8 or 10. That's really stretching it with Hubble. And this is how far after the Big Bang these objects existed when their light was emitted on this wide scale here. So okay, so Hubble gets us pretty far, but not far enough. And so in this slide, which was made by NASA a few years ago, we have the future, the James Webb Space Telescope, and they very cleverly did not put a date on it because, as you know, the date shifted. So okay, so Webb is going to be the ultimate time machine, and you know, it really, you know, we know it lives up to that reputation. But this is what Webb is, or at least this is the artist's impression before it got launched. This is what it was going to look like. And we are going to know. We knew that it was going to launch anytime now, and you know, really. And in fact, so that when I mentioned I spoke to you guys 2007 October, 15 years ago, and I gave this talk. There are some slides from this talk, and I talked about the future. I talked about the present, but I had a few slides at the end talking about the future. And in that slide, and I had some illustrations later on, but in that slide, I talked in that part of my talk, I had a slide which talked about ALMA, which is a radio telescope in Chile. I talked about TMT, and I talked about James Webb. And at that time, 15 years ago, I was confident that it's going to launch in 2013, and so were we all. And well, it didn't, and we had to wait another close to a decade. We're still waiting for TMT, by the way, but we still don't know a date. But okay, so it's been a long wait, right? And it's been, as Judy mentioned, 2 decades for me. But then this happened, and it did launch almost a year ago now, December 25th. Successful and spectacular beyond belief. Everything worked, right? There was the famous 15 days of terror, as they say, right? When you land a spacecraft on Mars, there's the what do they call it? The 5 minutes of terror, when you hope that everything goes according to plan and all the engineering works. Well, Webb had a few weeks of terror when everything had to deploy correctly, and there were multiple points where things could go wrong, and nothing went wrong. And that's just an amazing testimony to the incredible team that built Webb, and the delays were worth it, in other words, right? So that was a year ago, almost launched. Then we had a 6-month commissioning period when various observing modes of the observatory were tested, but no data were made available, at least to general public astronomers like me. And then in mid-July, we had the press release and the public data release of the first images from Webb. And you know, I'm sure you remember the various images that we saw. But the very first image that was released was this. This was released actually in a press conference, not quite sure what to call it, by President Biden, because he had to get his piece of the action. So the night before the official release of the half a dozen or so observations, the White House butted in, and they released this image. And this is gravitationally lensing a galaxy cluster, SMACS 0723, that I love the name. And so you can see here is the central galaxy in that cluster. Some of these white fuzzy things are galaxies in the cluster. And then there are galaxies that look like stretched out bananas that are gravitationally lensed by the cluster. And they're actually behind the cluster, right? And what's amazing about this image is, first of all and foremost, is that just how spectacularly good it is. Right? Webb really delivers. So let's see if I can zoom in here, and I'm sure that many of you have zoomed in on this image and looked at the various details, and it's just phenomenal. right? And it confirms what we know from the engineering data, that the observatory is just working superbly well. So I'll draw your attention to this object here. This is actually what caught our attention. We actually were in the middle of a team meeting for the nearest science team here in Halifax, and we were looking at these images, and we spotted this strange object, and we got interested in it, and I'll talk about it later. Okay, I'll come back to this. Okay, but the talk is about NIRISS. So what is NIRISS and what does it do? So NIRISS is the Made in Canada science instrument on board James Webb, and the acronym kind of explains what it does. If you know, if you know the technical terms, it's the Near Infrared Imager and Slitless Spectrograph. Okay, so near infrared, okay, it's easy enough. Near infrared is the wavelengths of light that are not visible to the human eye, but are slightly redder, slightly lower energy. It's basically heat radiation. Okay, the whole James Webb is optimized for near infrared observations, so it's no surprise that NIRISS is also optimized for near infrared observations. And we need that because that allows us to observe these very, very distant objects, which are red shifted into the near infrared. So if we want to study distant galaxies, near infrared is good. Okay, so near infrared imager, well, imager, okay, takes images, good. And then slitless spectrograph. Okay, so that last bit, slitless spectrograph, requires a bit of unpacking, right? So what the heck is a slitless spectrograph? Well, first of all, what is a spectrograph and what is spectroscopy? Spectrograph is, and again, you know, maybe you know, I'm talking to the converted, or not the converted, but the knowledgeable audience here. But let's just remind you that set the stage. What a spectrograph is it takes light, splits it into its constituent wavelengths, essentially into a rainbow, and then allows you to, once you've done that, it allows you to study what are the various chemical elements essentially present in the object you're trying to look at. So here we have a source of light, and if it can shine towards you, you're down here, and so what you will see if you put it through a prism, you'll see a rainbow, right? Because of the different colors of light, and the near infrared would be over here, just past the red, invisible to the human eye, but visible to our detectors. If you shine the same light into a cloud of gas, excite the atoms of gas in there, and then as they de-excite, they will emit specific wavelengths. Quantum mechanical processes make that so. They will emit specific wavelengths, and that's so instead of having a nice rainbow like that, what you will see is discrete light at discrete wavelengths, and that's super useful because it tells you about the composition of that gas cloud, right? What chemical elements are present in it, and then you can also, if you happen to be observing from this direction, you can also have that continuous spectrum go through the gas cloud, and then what you'll see is you'll see the spectrum, the continuous rainbow, but you'll see absorption where photons are taken out of the beam when they hit those atoms in the gas cloud. So you can also get some information about the composition of the gas cloud from that, right? And there's more you can learn from this. It's not just the composition, the chemical composition, right? Is there hydrogen, oxygen, and so on present, but how much there is, what's the temperature of the gas, and other properties. What's the density, for example? In particular, what's really interesting. So here's a model. Here's a, I'm an observer. So my theoretical models are very simple. Here's a galaxy that consists of old stars and young stars, right? And that's interesting for us. We want to know how many old stars a galaxy has, because that tells us how massive it is. We also want to know how many young stars it has, because it tells us how many new stars it's formed very recently. So these two things are related, right? The new stars are telling you what's it doing now. The old stars must have formed in the past, so it's telling you what it was doing in the past. So we want to be able to see how many old stars it has, how many young stars it has. The young stars basically have these gas clouds around them, and they're so hot, the stars are so hot that they excite the atoms in those gas clouds, and they give us these spectral lines, whereas the old stars don't do that, right? So what you would see is, you would see, you know, back to this picture, you will see for the old stars, you'll just see the continuum, and then for the young stars, you will also see bright spectral lines, and they're superimposed on each other because we can't really tell. You know, the stars are very intermixed, so that we can't tell where they are in great detail, but we can see, we'll see a combination of continuous spectrum, which tells us about how many old stars the galaxy has, and bright spectral lines, which tells us how many young stars it has. So good. So that's a way to tell us how big a galaxy is and how quickly it's growing. That's super interesting. How big it is, how quickly it's growing. Right. Okay, so if we have a spectrograph, we can do this. And most telescopes have spectrographs, but where NIR is special is that it's a slitless spectrograph. And what a slitless spectrograph does is something a little bit different than what normal spectrographs do. What normal spectrographs do, so here's a picture of the cluster that Webb observed. And what a normal spectrograph would do is would take a spectrum of one galaxy and maybe another galaxy and another galaxy, and that would be it, right? But what a slitless spectrograph does is it takes the spectra of every galaxy. And so here's the image in one particular filter of the cluster, and here's a nearest spectrogram of a chunk of this region. And what you can see is that this galaxy here is stretched out into a little spectrum over here. This one is stretched out into a little spectrum over here. And in fact, all the sources of light here, all the galaxies and also stars that are in the foreground are stretched out into these little spectra. Some of them are overlapping, which is a bit of a pain, and we have ways to deal with that. But right, this one and here and this one and here are on top of each other. But we basically get a spectrum for everything in this field. So thousands and thousands of galaxies we can get spectra for. So that's really great. Right? Oh, and by the way, you can see these emission lines here that I was talking about, right? So these are from produced by the gas regions around young stars, and you can see continuum, the long elongated stuff. That's from the old stars in this particular galaxy here. Okay, so here's another, and this. So the previous image was made by NASA in Baltimore. This is an image that a postdoc working with me here in Halifax made. So here's a distant galaxy behind the gravitational lensing cluster. So you can see there's some purple, some blue regions, and so forth. And here's the images of that galaxy. Well, let's just look at the top row. We have actually the image of the galaxy and then a nearest spectrum here. And you can see that this part corresponds to this part, and then this little blob here corresponds to this, right? And there's other things you can identify. And that's in 3 different wavelength regions. So that's the same galaxy here at shorter wavelengths, intermediate wavelengths, and long wavelengths. You can barely see it here. But it's the spectral lines here are oxygen, so doubly ionized oxygen, and hydrogen. And we haven't done it yet, but that will allow us in the future to determine the chemical composition of this galaxy. Is it a young galaxy which is not enriched in heavy elements, or is it an old galaxy which has had time to produce several generations of stars? Okay, so that's one thing that NIRISS can tell us about distant galaxies. Let me tell you a little bit about what else it can tell us. So this is that same galaxy, but now, sorry, the image is not very bright, but it's that same galaxy that has that central part. It has the little blobs here. And so let me just go back here, right? That central part, the little blobs here, here. And now, so what Vince has done here, Vince is the guy, the postdoc who is working with me on this. What he has done is he's divided this galaxy into several regions labeled by letters. And by using the spectra from NIRISS, he can, looking at the shape of the spectrum, he can try to determine what is the formation, the star formation history of that region? When was it making stars? Right. This is a galaxy that's observed about 4.5 billion years after the Big Bang. The universe is now almost 14 billion years old. This galaxy was at high redshift. It was observed it was emitting its light when the universe was only 4.5 billion years old. That light is getting to us, and what we're doing is we're looking at the nearest spectrum. I'm not showing the spectrum here, but I'm showing you where the information is coming from in the direct image of the galaxy. So you can see, for example, oh, and I should say that each of these panels is over here is the age. The Big Bang would be on the right-hand side. This is when we observe the galaxy, and today will be over here, but we don't, of course, know what happened to that galaxy after its light was emitted. But this is time going from right to left. Over here is the rate of making new stars in how many solar masses per year, how many new suns per year this region age. So where is that? That's here, over here, is making. Let me just go to one more slide forward. The regions are color coded here. So the different colors code the region. So age is this kind of dark brown or brownish reddish area here. There's also this region here, D and K, which have different histories, right? So age over here was making stars more and more and more. Then it had a little bit of a quiescent period, and then it started to ramp up again, right? The core of the galaxy, region I, which is over here, did something similar, right? But look at this, A, B, and C, which is sort of the more diffuse regions of the galaxy. They were increasing their star formation rate. They peaked about 1 billion years before the galaxy was observed, and then it started to drop, right? So now there's not a lot of star formation going on in this region here. And then you look at these regions D and K. Where's K? Let's look at K. K is this one here. Oh, nothing. And then very recently it started to ramp up and going crazy in terms of how many stars it's making, right? So that's K and D as well. Where's D? Similar, right? So we can look at this galaxy, break it. So this is the galaxy again. We break it down into its various components, and then we can tell when the various components formed, right? How this galaxy was put together. That's the power of nearest. We can get that information out of it. Okay. All right. And not only that, but we get a spectrum for every galaxy in the field. So we can do this for hundreds of galaxies in one observation, right? So this is just one galaxy. We're just starting this work. So this is stay tuned. There'll be many more. This is just preliminary results. We're just developing the techniques. Okay, so let me tell you about Canucks. So Canucks, what is Canucks? Canucks is the program that the nearest science team is doing. Right? So it stands for the Canadian Nearest Unbiased Cluster Survey. So we had a fun time coming up with that acronym. And here's our logo. And what Canucks will do is it will observe 5 clusters like the one that was released by President Biden in the press release in July, but we'll do so better and deeper, right? So the press release, the public release data are very nice, but our data will be deeper, right? We'll have more photons per cluster, and we'll have 5 clusters. And right, so what are the goals? Well, there's gravitational lensing, and I'll talk about that in a sec. That magnifies the galaxies behind the cluster, and that's what the galaxy we want to get at. So we're combining the power of Webb and the power of gravitational lensing to really look at the details of distant galaxies. And we're going to search for the first galaxies that have formed after the Big Bang. That's number 1. Number 2 is study how they subsequently grew over time. And I think you saw how they, in that example I gave, how we can tackle that second question, right? We can start to see how different parts of a galaxy formed, what is their formation history for the different components. Okay, so our first Canucks cluster will be observed in mid-October, so in 2 weeks. And that's assuming the Artemis launch does not mess us up, because Artemis, that's the new NASA heavy lift rocket. They will be using the Deep Space Network for communications, and they'll have such a high data rate that James Webb may have to slow down its observations. So if the launch is delayed, they're having issues. If the launches happen soon, then we may get affected. Then we have 3 more clusters in the winter, and then we have the 5th cluster in May. So, stuff will happen pretty quickly. But we don't have any data yet, right? We don't actually have any data yet. So we don't have any data. This is the Canucks team. So why are we smiling? I've circled, so this is the Canucks team. I've circled the people who are St. Mary's folks. Vince is the guy that I was showing you, that galaxy broken down into its star formation history by component. That's him. And then there's other folks here. And then there's the whole team. We had a few people who couldn't make the meeting. This meeting was actually in Halifax in July. And so that's the team. And so why are we smiling? Well, we have not been sitting on our hands waiting for our Canucks data to come. We've been analyzing these data from the public data release, right? The cluster that, as I jokingly refer, President Biden released. So and so I'm going to talk about the sparkler. Okay, so the sparkler is that galaxy that I told you that I'll come back to later in that cluster, and it's this one here that caught our attention, right? And we decided to. This was back in July. We decided to go and run with it. So here's what it looks like with Hubble. Right? If you look at the same field with Hubble, this is what you see. Pretty boring. When you look at it with Webb, and this really illustrates how good Webb is, you see this, right? So you see these things around it, these yellow things around it, which we call the sparkles. And our hypothesis was, are these globular clusters? Right? As you probably know, globular clusters are our own galaxy has about 150 globular clusters. These are thought to be some of the oldest bits of our galaxy, and they look like this. This is a galactic globular cluster in the Milky Way. Tens or hundreds of thousands of stars, but very compact, and also very old. Right? Hard to tell how old, because it's very difficult to get a good age on something that could be as old as 10 billion years or maybe 14 billion years. Right? It's like looking at somebody and saying, well, this person is middle-aged, so maybe they're 50, or maybe they're 45, or maybe they're 55, right? And Judy had a problem age dating me. And so, but it's much easier to tell that, so 50 to 45, hard to tell, right? 5-year difference. But if you look at a kid, right? If you look at someone who is young, you can really tell the difference between a 5-year-old and a 10-year-old very easily, right? The same 5 years difference with a child, you can tell right away. So if you look at a young system, right? So looking back in time, lets us look at a system when it's young, we can tell how old these things are, right? The globular clusters in the Milky Way, yeah, they're old, but we don't know how old, not precisely enough. Here we have a chance. So that's what we decided to run with this thing. Okay. Now, what's helping us? I mentioned gravitational lensing. These clusters, so this public release cluster, as well as the Canucks cluster that are coming, they're also massive that they gravitationally lens the light behind them. And this is sort of a picture of it that tries to illustrate that. So if you have a distant galaxy, you're over here on Earth. Here's the cluster that's gravitationally lensing, and there's a distant galaxy behind it. What happens is that the light from the galaxy, of course, goes in all directions, but it also goes towards the Earth. But not exactly towards the Earth, right? It travels this way. Normally it would travel in a straight line, but the gravitational lensing by the mass of the cluster bends the light and it reaches the Earth from this direction. And on the other side, it reaches the Earth from this direction. So you can have multiple images of the same galaxy. And that is in fact what happens in this cluster and with the sparkler galaxy. So this is the sparkler, and this is another image of the same galaxy. And this is the third image of the same galaxy, here, here, and here, right? They're distorted in different ways by the gravitational lensing, but that's the same galaxy. And I'll show you in a bit how we know it's the same galaxy. It took a lot of fun and hours, but here's the 3 images zoomed in. That's the sparkler, the main sparkler, and that's image 1. And then image 3. And some of these yellow things are the same yellow things in this picture and in this picture and in this picture, right? And that's actually what you see here. That's that image, the main image, That's the first image, second image, and that's the third image, and that's what we call the second image, which is the main image. And the numbers here correspond. And I had a lot of fun in August matching these up, trying to figure out how they match up. And what really helped me, so these are images from Webb, but this is nearest data, right? And it's the nearest data that really helped me, because I looked at, so this is the image 2, here, this is nearest. So this is the oxygen spectral line, characteristic of young, it's produced by young stars ionizing their or exciting their surrounding gas, and then we see it, and we see it here, and we see it here. And at first I was trying to match up things in this image between these images, and I was having a hard time, right? There's just so many things. And then Vince made this image, right, from the nearest data, and I went, okay, so this thing must be this thing, star forming region must be this thing, and over here in the color image, and it must be this thing here. So boom, right away, here, 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 and then everything else fell in place, right? So nearest came through for us here. So okay, so we now know why was this important? This was important because, you know, you could say, well, how do you guys know that these little yellow things are actually associated with this galaxy? They may just be something else, maybe in front of it, maybe much lower redshift. Well, if we see them in this image and in this image and in this image, and we're confident they are the same object, then they must be associated with the main galaxy here and here and here, right? That was crucial. So nearest came through for us. And then once we knew that, we looked at these objects. So here they are again. This was work by Karthik Iyer, University of Toronto, another Canucks team member. And so we measured their brightnesses in different wavelengths, and then Karthik fitted their star formation history. So how many stars was each of these little sparkles making as a function of time, right? So let's take this panel here. This is look back time again. Right, we're observing this galaxy about 4.5 billion years after the Big Bang, and this curve here shows you how rapidly it was forming stars. So this is number 9, ID number 9, this one here, and this one looks like it had a peak around about 500 million years after the Big Bang, and then it declined. Right, but if you look at and this one here too, number 11. So that's this one. Where's number 11 gone? No, sorry, number 10. Number 10, this one here, had a peak around 500 million years after the Big Bang. The Big Bang is right here on the edge, and then it declined. And others had a kind of more, slow start, and then they had a peak maybe around 3.5 billion years after the Big Bang, and then they went down, right? There's 1, 2, 3, 4, 5, and this one is not colored in pink. For some technical reasons, we're slightly less confident about it. But these 5 here were confident, had this rising phase that was very rapid after the Big Bang, a peak around 500 million years after the Big Bang, and then a declining phase, right? So it's these pink ones here. And what's that? So these objects formed very early on in the history of the universe, right? The universe was born here, and then they started forming stars. This one, this one, this one. You can see this pattern repeating, rising up, peaking at about 500 million years after the Big Bang. So when the universe was only 3 or 4% of its current age, and then declining, right? So these are very, very old objects. Most of their stars were formed very soon after the Big Bang, and we can say that there are globular clusters in this galaxy that formed 500 million years after the Big Bang, very, very early on, right? So that's why we can make the statement, we found some of the oldest stars, oldest star clusters in the universe. Okay, so that's the story. There was a press release on this actually on Thursday. Here's the picture that CBC News decided to use instead of the one I showed you where we're all smiling at the camera. They thought this was clever because it makes us look like the Last Supper. And there's this story. James Webb's Space Telescope reveals some of the oldest stars in our universe. So if you want to read about it more, you can, or you can ask me, because this is the end of my talk. So I'm going to stop here and just leave you with this picture, or maybe I'll stop sharing and we'll go with questions.
Thanks so much, Marcin. Boy, no wonder you folks are excited about what you're getting, the data you're getting. Thanks so much for this. I'm going to open up the floor for questions. You can do it one of two ways. You can either unmute yourself or put them through the chat, and I will pick them up through the chat for you. Either way. I have a question for you, though. The very broad way in terms of the research, the data that comes from Webb, is that privileged property of NASA, or, like, for instance, when you folks were all working on this over the past 20 years, were there requests for specific types of data? This is what you want to look at. Do more than one group get the data? I know it's a lot of questions all at once.
Yeah, I know what I know what you're trying to get at. Yeah. So there's several different ways to get data from Webb. You can write an observing proposal and say, I have this great idea. I want to observe things this way, and da 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 da. And this you submit. There's a deadline. Lots of teams submit their proposals, and there's a competition essentially. And the best proposals get picked. And you can also do what we did, which is be involved with the instrument for a long time, and then as a reward, the instrument teams get data without having to go through that competition process. So that's how the Canax program is actually. That's how we will be getting our data, is through the rewards program, and that allows us to actually get a large amount of data. We are one of the biggest programs on Webb, 200 hours of observations. Okay, now is the data public? All data from Webb and from Hubble, this is NASA policy, and it's actually, many observatories do that as well. Ground-based observatories do that as well. The data becomes public a year after they're taken. So anything that's observed, the science team that proposed for the data has 1 year proprietary time, and then the data become public. Some teams waive that time and make the data public right away. That can improve your chances of getting approved for your program, because the selection committee looks like, oh, well, this may be useful to other people right away. So that's a plus. So many programs on Webb actually have their data released immediately, but not all. And the other ones keep it for a year to themselves. And then there's also the so-called early science observations, public observations, which like that cluster that was released in July, which was done specifically. It wasn't proposed by a specific group of scientists for their own research. It was just done as essentially a publicity, to demonstrate the power of Webb. And that was also released right away publicly, so that everybody can jump on it, like we did with the sparkler, and go crazy. So there's stuff out there. If you want to get your hands on Webb data, you can. It's anybody in the world can do it. There's data there's in the archive now that are public.
Right. So I know we'd have to wait for a year for those that are proprietary.
You don't have to wait. We did not wait for the sparkler for the first cluster. Yeah, that came out right away. Yeah.
Okay. A comment from Lisa Ann saying, "Great talk, thank you. Congrats to the team. Excited what is to come." I guess which could lead to the next question. When do you anticipate publishing what you're finding?
Well, so the sparkler was published already. And so that's published. We have a few more papers in the works on that first public data release cluster. But I don't want to say when exactly we'll get them published, because work can take longer than you think. And then once we start getting our Canax data, we'll go crazy. And so our goal is to have a lot of papers out before that first the first year is up, right? Because then other teams will download the data and start they can scoop us. So we wanna make sure that we get some of the most sexy, exciting science done in that first year. So basically, that puts the onus on us to get as much done and published by about Christmas of next year.
Wow. No hurry.
We'll be busy. No, but I should say, we have an awesome team. We're not a very large team by Webb standards. I know there are teams that have literally hundreds of people. We have about, well, you saw that photo, right? So there was a few people not in that photo. There's a couple of them were on Zoom, and you could see them in one person was holding a laptop with two people in there, and there was one or two others who just couldn't make that meeting at all. But we have a maximum of 20 people, so we're not a huge team, but actually many of us are here in Halifax. So about a third of the team is in Halifax. There is 3 people in Toronto. There is a few in Europe, 1 or 2 in the US. But we're very, the team works superbly well together. And I will tell you that writing that sparkler paper, that's the galaxy with the globular clusters around it. It was some of the most fun time for doing astronomy for me. We basically wrote that paper in 2 weeks, and it was all done on Slack. I don't know if you know Slack, but Slack is a collaboration tool, a remote collaboration tool, about a week of staying up till 3 o'clock in the morning for me, but yeah, it was really intense and really fun, and I want to do that again. So and I think the others do too. So yeah.
That's great. Thank you so much. Any other questions for Marcin before we go on to our next speaker?
I have a question about the spatial resolution in the 2 example galaxies that you looked at. You have subdivided those into various areas of interest. How does that area relate to the resolution of the data you have?
Yeah, well, that factors into it. We obviously cannot see on scales that are smaller than the resolution that the telescope gives us. Webb spatial resolution is in the infrared is as good as Hubble is in the optical, which is extremely good. But still, we can only split say a typical galaxy in the distant universe. We can only split it up into maybe 6 or 7 resolution elements in one direction. What we're doing with Canucks is we're going to gravitationally lensing clusters to get an extra boost, because the gravitational lensing, as you saw with the sparkler, right, there was 3 images of the sparkler, and one of them was highly elongated. That's not how the galaxy really looks like, right? The galaxy is more like a normal spiral galaxy. That was maybe I'll share. So that's the sparkler here, and the galaxy probably looks more like this. This is somewhat magnified compared to this in terms of pixel scale, but the lensing takes this and stretches it out this way. So we have super resolution along this direction, right? In addition to what Webb gives us, which is already very good, we have this stretch here. So each of these clusters has many arcs, many lensed galaxies like this, where we have the super resolution, and we have 5 clusters. So we can go down to very small scales. We can go down to we think in some cases we'll be able to go down to a few hundred parsecs for galaxies that are, when the universe was let's say a third of its present age, as is the case for the sparkler. So we can really stretch it out and get really, really good resolution.
With that image in the center there, what is the actual resolution of those pixels? Are we seeing that at full scale, or is there more data available?
So yeah, this is a bit blurred by the JPEG. Here, what you see here, so this is a single wavelength image, and so you can see the pixels, I think, here. These are, if I remember, because we have images at 2 different resolutions, pixel scales, but these are, I think these are 40 milliarc second pixels, so 0.04 arc seconds per pixel. And I think so. We also have we actually have images also at double the pixel scale. It doesn't give us extra resolution in terms of sharpness, because that's defined by the optics of the telescope, not by how big your pixels are. So sometimes we use bigger pixels, sometimes we use smaller pixels, but this post-processing for these images. But yeah, these are 0.04 arc second pixels. Right. So for comparison, ground-based seeing in Halifax is about 2 arc seconds. So a star in an image from the Burke-Gaffney Observatory at St. Mary's Campbell's would basically fill this whole image, just smeared out.
Great, thank you.
So badly. Yeah.
Okay. One of our excuse me. One of our members, Bob Russell, comments, "Super presentation, Marcin. I'm excited about your work too. We'll be watching for more sparklers. Thank you."
We have another sparkler. I'll give you a little preview here, because it's if I can find the right image here. I'll give you a little preview. So that first sparkler. So oops. Here we go. So that first, the original sparkler is here. Okay, and then this is the counter image, and there's the third counter image. Now, if you go over here, look at this galaxy here. I don't know if can you see the little dots in it?
Yes.
Yeah. So we don't know the redshift of this galaxy. The other one we do know, 1.38. This one we don't have a redshift for yet, which is why we're holding off a little bit. But we have an estimate of a redshift. We think it's at a similar redshift as that sparkler, but it's a much more massive galaxy. So this galaxy is if it's at that redshift, this galaxy is equivalent to Messier 87, M87, which is a very massive galaxy in the nearby universe, except it's seen when the universe was only a third of its present age. And it does have these little sparkles here, many, many more than the first sparkler, right? There's about 30 or so orange ones. Orange tell us they may be old, and there's about 30 of them. If this is like M87, M87 is something like 200 times more massive than the Milky Way, and has about 15,000 globular clusters. We may be seeing the tip of the iceberg of the globular cluster system of this galaxy here. So we're very excited about this, but we really need to be sure, and so we need to get a redshift first. And so that's I was writing a observing proposal last night for that. Yeah, so lots of excitement. Sorry,
is that a replicate gravitationally lensed image up to the left?
Oh, here?
Of what you were looking at,
okay, so
the one that you're interested in, at 10 o'clock or so, there's another smaller object.
10 o'clock here?
No.
Oh, sorry.
The two bright white stars on the left side, higher up.
Here.
To
here.
The left of that, yeah. Is that a replicate there?
Of this one? No. So our lensing people, and we have a lensing expert on the team here in Halifax and another one in Europe. We thought about it. In fact, we also thought that you take this galaxy here, and on the other side of the cluster, so we call this one Big Red 1. Why 1? Because on the other side of the cluster there is Big Red 2. and also has sparkles in it, and possibly even big red 3 with sparkles, but who knows. But the lensing, our lensing folks are saying, no, the geometry doesn't, no, it's not going to work. So these are not the same galaxy, these two, or nor is this one. This is something else, unrelated, possibly at the same redshift. If you have a massive galaxy like this is again M87. Is the local analog of this. M87 is at the center of the Virgo cluster. I think it's Virgo. Is it comma? I think it's Virgo. Cluster of galaxies, right? It's the most massive galaxies in the Virgo. Well, if this is an M87 analog at redshift 1.5, it should have a cluster around it as well. So some of these red things could be companions of this galaxy, but we'll have to see. We'll have to see. Right. The other thing that's also happening, there are other galaxies here that have sparkles around them. There is this one that's definitely gravitationally lensed. It's actually mirror imaged here and over here. And there's a team in Europe that wrote a paper about this one after we did now everybody got excited about, we put out this paper as a preprint about a month and a half ago, and then people got excited and started looking at these other things. Yeah, lots of fun stuff in this cluster, and we're really scrambling at some level because everybody's got these data, so everybody can put out a paper on anything in this. But when the Canucks data come, we have that year where we can sort of take a breather and do a really careful job without having to worry about being scooped. So that's tremendously powerful for us, having that proprietary time.
Yeah. So when or where will your paper be published?
So the Sparkler paper came out in Astrophysical Journal Letters. It actually came out on Thursday as officially published by the journal. You can go to the journal website and download it from there. But it's actually, I don't know whether it's behind a paywall or not. It may not be. But there is a preprint on Archive, which is the preprint server that's open to the world that we put out maybe a month ago. And if you're interested in having a look at the paper, I have if you go, Google for my name, and on my website, there's it's the news.
Wonderful.
You can get to the paper if you would like, and if you have some questions about it, fire me an email. I'll be happy to talk to you about it.
Yes, we can tell by the grin on your face you're very happy about this. I'll repeat what Bob Russell said, and I think he speaks for all of us when he said, "Wow, thanks for the sneak peek." This is really exciting, and obviously just the beginning of many, many more things to come. So I thank you for this.
You should in a year, you should get one of the postdocs who are here in for a talk and get them to give you an update. We
will do that. We will put that on the slate of speakers. Thank you so much. We'll be in touch, Marcin. So thank you again for a very interesting talk. And certainly
hope I didn't run too much over.
No, not at all.
But you can see it's exciting.
Yeah, I'm sure that when we start to look up, we'll be thinking about your paper and what it is that we're not seeing when we do look up. So thank you.
Thanks. I'm going to have to go. I'm looking at the clock, and I have to go because of my family.
Certainly. Thank you so much for joining us today and taking part of your Saturday.
But no, it was a pleasure. And, as I said before, I really enjoyed my talk 15 years ago. I enjoy my talk now. And I had many interactions. I see some names. Dave Chapman here. I had many interactions with a number of rascals over the years, and I hope we can ramp that up again a little bit more.
Yes, Mary Lou Whitehorn, who initially contacted you, is on vacation out west and was really sorry she missed your talk, but she does know it's recorded, so she will hear you.
Mary Lou is a good friend. Yes. Okay.
Thank you. Enjoy the rest of your day.
Thank you for having me. Will do.
All right.
Bye.
Bye. Okay. Back to gallery view here. Next up on our agenda is our second special guest, and that's Chris Young. For those of you that know Chris, he's been with us for many years. He's certainly helped me along my journey in astronomy and telling all sorts of neat and wonderful stories about the stars. And as you know, every second month, Chris comes up with a new batch of stories to tell us about other civilizations and how they view the stars. So Chris, take it away.
Okay, let's see. Oop. Is that full screen for you, Judy?
It is.
Great, thank you. So at the last meeting, Dave Chapman gave an interesting account of the naming of the moons with reference to the Greek myths. I'd been staying away from the Greek star stories, but I thought I'd revisit them and also have a look at the development of their constellations. This is a bit of a sort of a project in progress, and I sort of rely heavily on two papers by historian John Rogers called "The Origins of the Ancient Constellations." The zodiac is the basis of the Greek constellations. It was created in Mesopotamia from two earlier traditions, one where the constellations represented the gods and their symbols, and the other set represented rustic activities and provided a farming calendar. Many constellations were shared by the two traditions, but there were also alternate figures. These figures developed in stages from about 3000 to 500 BC, with the divine set, the 12 zodiacal signs, and some animals were the last to be finalized, and these were transmitted to the Greek sky map around 500 BC. This is what we use today. The rustic tradition constellations of workers, tools, and animals was not transmitted to the West. Some may have survived in Bedouin Arab sky maps into the first millennium. The Greeks assembled their classical sky map around 500 BC, and this included large constellations, likely from the Mediterranean region, devised for the navigation of ships. This included huge bears, serpents, and possibly 4 anonymous giants, Heracles, Ophiuchus, Butes, and Auriga. Many of the names and legends familiar to us were applied to these constellations later. So here we are, this is the Mesopotamia is located in this area between the Tigris and the Euphrates River, and Mesopotamia means the land in between. We have sort of Syria here, Arabia down to the bottom right, Egypt. Up above is the Hittite Empire, which is Turkey to us now. We have Greece on the top left here. This is Crete. And over here is Cyprus. Italy's just off the page. So there were large distances involved in terms of traveling, and it couldn't have been easy, but there was a significant trade going on here. This is the late Bronze Age, around 1300 BC. And there was a lot of traffic. Most of it would be by ship, was the easiest way to travel, but a lot of goods, be they food goods, weapons, specialty items, precious metals, such as copper, shells, which were used for dyeing, all kinds of things. And no doubt ideas also were transferred back and forth. What we know about the Mesopotamians and their sort of kind of sky map mostly comes from the cuneiform tablets that we have left to us. But this is a boundary stone, which was essentially a property deed. It was kept in a temple, and it has carvings here on the top of it. The owner of the property would get a duplicate stone, which they kept, but this proved that they owned the land. But so they had to have gods and figures that would be carved into the top. Similarly, this is a seal that was used. The seal is about 4 inches high. It's a cylinder, slightly tapered in the center, and it was rolled across a wet clay tablet to give you an imprint. And this was used for as a seal on storeroom doors or on bags or crates of goods that were traveling perhaps by river. And so again, we have some figures that we know to be gods. This is the Mulopin tablet, which is in the British Museum. There are two tablets that there's a pair. This makes a part of half of a pair, if you will. This is a large tablet. It's about 8.5 by 11, which is quite big compared to most of them. And this version here expanded on earlier star catalogs based on more accurate observations, and was likely compiled around 1000 BC and then was recopied. The text lists the names of 66 stars and constellations, and further gives a number of indications such as rising, setting, and culmination dates that help map out the basic structure of the Babylonian sky. Here's another tablet. This one's interesting in that it records Halley's Comet. This would be in about 164 BC. So they kept a lot of data. So the interesting, we recognize this as Ares the ram in the Greek stories, but in the for the Babylonians, this was the hired man, and in terms of on the rustic side, and then on if you will the sort of divine side, this was Dumazid, who was a god figure who was also associated with shepherds, agriculture, and date palms. And it was also called the hired man. And I got interested in this from reading a book by Krups, which you'll see the cover on towards the end of this presentation. And he stressed the importance of the hired man, or the agrarian worker, in working with date palms, because these were important food source. Date palms have been cultivated since about 5500 BC, and there are male date palms and female date palms. The males produce pollen, females go on to produce dates. But if you fertilize by hand, you can have like 4 male date palm trees and then a whole plantation of female trees. And then you collect the pollen from the male tree, and then you by hand, and you only have a 2 or 3 day window when the I guess the flowers are vital to pollinate them. And then so if we have a date palm grove in Qatar, and so this is early in their development. They've opened up, they've been pollinated, they're growing. And you'll note they have these 4 or 5 inch barbs on the front, and apparently these will easily puncture a truck tire. So it wasn't an easy job. And then the dates go on to mature. So the sort of constellations were developed by the Babylonians. They were in the process, no doubt, the Greeks were becoming aware of them. And in a lucky find, there's a temple of Hathor in Dendera in Egypt, and there was a zodiac that was found there that included Babylonian, Greek, and Egyptian constellations. And this is the Temple of Hathor, taken about, well, before 1923, which is when the photographer died. It was a hand-colored photo. This has all been developed, recently. If you look up the Dendra Zodiac, you'll see interesting photographs. It's a large tourist attraction. It's a fabulous temple. This is inside, looking up at the ceiling. This has been recently cleaned, so they had centuries of soot that had caked up on the relief carvings, and it had been painted, so it was quite something. So the stone panel, the zodiac that we're interested in, was found when Napoleon invaded Egypt, and it was removed from the temple using chisels and crowbars and a bit of dynamite, and taken off to Paris in about 1821. There was some argument over the date of the temple, and this is its creation. But apparently there are two eclipses that are encoded in the figures that we see here. So these, when the zodiac and sky figures have been transferred to Egypt, they became kind of Egyptianized, and the gods often had similar attributes. The Egyptian gods had similar attributes to the gods that were found elsewhere. And here is a more simplified version, and here's the hired man and our ram, if you will. So anyway, so this John Rogers characterized this as the only complete map that we have of an ancient sky, and is probably the basis for our sort of star system or our sky maps. So, and then here's a further distillation of that same zodiac, where they found 72 constellations, which includes the 48 Greek constellations of Ptolemy, some southern constellations, and some other ones which aren't recognized by the International Astronomical Union. So the constellations then around this time in Greece had sort of settled to the ones that we know today. And over time, they applied new stories to them. And one, here's, in this case, we have Aries. This is an illustration taken from the Flamsteed Atlas. And Aries is the golden ram that rescued two children, Phrixus and Hele, on the orders of Hermes. The male child was to be sacrificed by his father, the king, following a false message from the Oracle of Delphi, stating that the sacrifice was necessary to end a famine. The famine was created by his second wife, who hated the stepchildren. Aries was sent more directly by Nephele, who was the king's first wife, and arrived and carried the children off. The daughter fell and drowned in the Dardanelles, the channel between Europe and Asia, which the Greeks named the Hellespont in her memory. When he reached safety, Phrixus sacrificed the ram to thank the gods, and Nephele placed the image of the ram amongst the stars. There's another ending to it, which is because the ram was thought to be immortal. It shed its own fleece and flew into the sky. Either way, the lack of the radiant fleece was said by the mythologists to account for the constellation's relative faintness, which is an insight I hadn't thought of. So another story, which most of us are familiar with, is the creation of the Milky Way. And we know the story, which is shown here in Tintoretto's painting, which is, so here Zeus was kind of a known womanizer and often seduced mortal women in various disguises. Alchemy was one of his victims, and he tricked her by appearing as her own husband, which is quite a low trick. Zeus was very fond of his son Hercules, who was born from this liaison. He wanted to render him immortal by letting him drink milk from the breast of his own wife Hera while she was asleep. But Hera was awakened by the suckling infant and pushed him away, and the spilt milk of the goddess became the Milky Way. So most of us knew this one, but I found another story, which was of Rhea and Kronos. And Rhea was the older sister of Kronos, but was also her consort, and the mother of the 5 eldest Olympian gods. But Kronos, who is the ruler of all the gods and men, learned that he was destined to be overthrown by one of his children, just as he had overthrown his father Uranus before him. So he swallowed all the children Rhea bore as soon as they were born. When Rhea had her 6th and final child, Zeus, she spirited him away and hid him in Crete. Rhea gave Kronos a stone wrapped in swaddling clothes to swallow instead of his son Zeus. Kronos asked Rhea to feed the child to prove it was her own, and she pressed some milk from her breast to show him that she had really given birth, and it formed the Milky Way. He swallowed the stone. Zeus went on to become a young man, and as destiny was going to be fulfilled, overthrew his father by poisoning him with a poison that made him vomit up all the other previous 5 children, who miraculously had all matured while they were inside Kronos. Here's a figure that you will recognize. It's small, just outside the summer triangle. So this is Delphinus, the dolphin. So Poseidon, who was one of the children of Rhea, he established his kingdom, if you will, in the sea, and he built a great, terrific palace there. But it felt empty because he didn't have a wife, so he set out to search for one. He courted Aphrodite, one of the group of sea nymphs called the Nereids, but she fled from his rough advances and took refuge amongst the other Nereids. Poseidon sent messengers after her, including a dolphin, which found her and whose soothing gestures brought her back to the sea god, whom she subsequently married. In gratitude, Poseidon placed the image of the dolphin amongst the stars. Now, there's a second version that explains the dolphin in the sky. And this is the map that we have born. And we're talking about a very talented musician and poet who came from Lesbos, who worked in the court of the king of Corinth, and apparently his abilities with his kithara, which is a 7 or 8 string lyre, and his voice said that he was unequaled anywhere. And he got permission from the king to travel around the southern Italy and Sicily and the islands to share his music, and he collected some riches along the way. So when he was returning to Greece by ship from a concert tour in Sicily, and here we should go. So here's a cithara player. Cithara is also, I think, the root name for where guitar came from. There's a detail, and apparently the number of strings gives you some idea as to the quality and the skill of the player. Anyway, he was returning from back to Greece. Some sailors plotted to kill him and steal the riches that he had earned. Apollo appeared to him and told him to sing in his robes and crown and entrust himself to those who would come to his aid. When the sailors surrounded him with swords drawn, Arion asked to be allowed to sing one last song. His music attracted a school of dolphins, which sang alongside the ship. Placing his faith in the gods, Arion leapt overboard, and one of the dolphins carried him back to Narium, which was one of the spots there on the map where he was saved. Apollo, who was the god of music and poetry, placed the dolphin amongst the constellations, along with the lyre of Arion, which was represented by the constellation of Lyra. Now, like most, as I say, Greek myths, there is another myth about Lyra, but that's as far as I'm going to take it today. So I'm going to. So these are some of my references. There's some papers here in the bottom right by John Rogers, Origin of the Ancient Constellations. These were available on the web. Another one by Rosalind Frank, which is a more modern one, which kind of supports John Rogers' description. The Beyond the Blue Horizon by Dr. Krupp got me started on this because it had the story of the hired man and Dumazid, the god. For reference for the Greek myths, I went to Aristophanes and Hyginus, the constellation myths. And another reference was James Evans' The History and Practice of Ancient Astronomy, which gives you some sort of scholarly background on overview of the development of astronomy in the Middle East. So that's it for me. And I should be able to give you back here, I think. Let's have a look here.
While you're doing that.
Oh, there we go. Where are you?
Tell you what.
I'm
How's
not
that?
seeing you. Yeah, that's good. Take over. You drive.
Thanks, Chris.
Thank you.
For that. I always find it intriguing that these Greek and Roman and that era type myths always involve secret trysts and murder and deceit and all that sort of thing.
You're right. It's soap operas on a grand scale, and one of the challenging things was every time I would try and follow a link and particularly on Wikipedia, I would find two more, and then there would be two more, and all of the characters had their own backstory. Nefeli, who was the mother of the two children that were rescued, one made it, one didn't, was formed out of a cloud by Zeus. Excuse me, yes, by was it Zeus? Yes, by Zeus. And because he had a visitor who was enchanted with his wife, Hera. And anyway, so he made this duplicate of Hera out of a cloud, Nefeli, to test his guest. Well, his guest failed the test, and she went on to bear a child who was, I guess, somewhat deformed, who then mated with a horse, which gave us all of the centaurs. That's where the centaurs came from. Like it just keeps going. Right? So, and I think Dave ran into this when he was trying to get a grip on the names of the constellations and what the stories were. But the history of the constellations is I'm intrigued with this, and we'll likely come back to it. Is that we can account for some of the constellations, the star figures. We can see the development of the figures as they evolve into from gods that the Sumerians had, and then the Babylonians had, and then the Greeks had, and the Egyptians also were a little side issue and stuff. But there's these other constellations which came from elsewhere, and we're not sure where they came from. Some of them, the larger ones, they thought were probably for use for navigation because they were larger and easier to see and used for navigational purposes. And then there's the dippers were seen as wagons. This was back at the time of the Sumerians. The wheel was invented around 4400 BC, we think, and so wagons would have made some sense before 4400 BC. Well, what were they then? And there's some thought, we keep coming back to bears. The bears keep showing up, and so they God knows, it may go way back in prehistory. Anyway, it's fascinating and distracting, and no doubt I'll share my fascination with you in the future. Anyway,
I think Jerry said, he says, thanks, Chris. Interesting rabbit holes.
Yeah. Oh, yeah. Fascinating, but oh my God, time consuming. Yeah. Goodness.
Yeah. Well, thanks again for that. That was enjoyable. Interesting stories as always.
Oh yeah. They're rowdy. Those Greek myths are rowdy.
Okay. Next up, and I apologize to Jerry for having missed him earlier on in the agenda, but David Hoskin had provided Jerry with the photo montage. So Jerry, I'll let you show what David has put together.
Okay, I'll try and share my screen here. And go back to the top and see what I can do. So this is, can you see that, Ben?
Yes.
Okay, so in theory, these are the images that he had collected from both Facebook and I think the listserv in the last month. And we'll just let them play. They're not all mine, so.
Oh, wow.
Very, very interesting.
Especially through a window. Wow.
That's phenomenal.
Oh,
Yeah.
Apparently it was white, naked eye.
Yeah. Neat, David.
Phyto, I've never seen that before.
Oh, wow. Perfect capture there, eh? Interesting colors. Neat.
That's pretty dramatic.
Oh, beautiful, Lisa Ann. Neat. Three of the four moons. Oh, and David's solar captures are always amazing.
Not sure where the engagement ring is on that. I'll have to look that up. That's phenomenal.
Yeah, it even sees the red spot there. Wow. Great. Thanks, Jerry. Looks like our members are doing some phenomenal photography. You know, in all different aspects of it. Everything from deep sky to a wide field. It's beautiful. Thank you. So, which then leads me to Lisa Ann Fanning, who is going to do the What's Up for us this month. Lisa Ann?
Yeah, I'm just trying to find. There we go. Oops. Can you see that?
We can.
Excellent. Let's see if I can move this out of the way. Okay. So what's up in the sky? I hope I can do it justice the way that Dave Hoskin does it. But so I woke up this morning with my allergies like clockwork. So I know it's October. That's how I knew. For the sun this month. Really happy to see that we are getting much more darkness. For those of us who don't like to stay up too late, who appreciate our sleep and have to get up early in the morning for work, at least we could start to do some of our imaging and observing earlier. So today, sunset will be at 6:54 p.m. with dusk end at 8:31. As we get to the end of the month, we're looking at sunset at 6:04 and dusk end at 7:43 p.m. So by the end of the month, we end up with 10.5 hours of darkness. For the moon this month, first quarter, this is the Wiki-Wee-Goose cycle of phase of the moon. So we hit first quarter on October 4th. October 5th, we have the moon, and Saturn is 4 degrees north of the moon, so a good opportunity there to see the two together. On October 8th, Jupiter is 3 degrees north of the moon. October 9th is the full moon. And then October 12th is the moon in Pleiades, where Pleiades will be 3 degrees north of the moon. So a nice opportunity there to try and capture those two together. October 14th, moon and Mars. We have Mars 3 degrees south of the moon. On October 17th, the last quarter moon. And then October 21st to the 22nd is the Orionid meteor shower peak, which is just prior to the new moon on October 25th. And that is the Keptikawigous river freezing over moon. And then I would be remiss if I didn't mention that tonight is International Cloud Night in New Jersey, and the rest of the world, it is International Observe the Moon Night. So you can go to moon.nasa.gov, observe the moon night, and see some of the opportunities there. I did get an email from NASA, so I think much of the East Coast, at least, is going to be weathered out. I know we're getting the remnants of Ian, but so NASA was looking for folks who were willing to run virtual tours of the moon. So you could still participate just behind the screen tonight if you're weathered out. So take a look at that website. So here's what I mentioned for October 12th. This is at 10 p.m. There is Pleiades just north of the moon. So that's a great opportunity. I think I'll be trying that challenge. Hopefully I have good weather. And then taking a look at the moon. This is the moon in Explore the Universe. So some of the craters that you'll want to take a look for in Explore the Universe, as well as Explore the Moon. We have the challenges. Those 12 craters are listed in those challenges for those programs. So first quarter is always a great opportunity to take a look at those craters, many of which appear on the first quarter moon in good relief. And then the mare are listed there as well. So October 2nd through the 6th should be best opportunity to see many of these features for those programs. All right, let's take a look at the planets this month. So Mercury is very low in the pre-dawn sky, difficult to see after mid-October. It reaches greatest western elongation of 18 degrees on October 8th. Venus is currently too close to the sun to be visible, but the good news, Mars rises before midnight and brightens to magnitude negative 1.2 by month's end. It is close to the moon, as I mentioned, on October 14th. The next opposition of Mars is December 2022. This is a good time for zodiacal light. It's visible in the eastern sky before the morning twilight, starting in October. And Jupiter will be visible throughout the night all month long, magnitude negative 2.9, close to the moon on October 8th. I know a lot of people have been out there imaging Jupiter. The other night I was out there and got a great look at 3 of the moons that formed almost a triangle just by Jupiter, and also got to see the great red spot, so that was exciting. Saturn is rising before sunset. It's well placed in the evening for evening observing throughout the month. So take a look at Saturn as well. Uranus is visible for most of the night. It's at magnitude 5.6. It's also close to the moon on the evening of October 11th and after midnight later on in the month. And then Neptune is visible for most of the night, magnitude 7.8. So you'll need some bigger optics there. That's my current challenge personally. Here's some other challenges that David has issued. October 11th at 11 p.m. Here's the challenge of Uranus just below the moon, and then zodiacal light, October 23rd to the 31st before dawn. This is a good period of time for that. Okay, so we have Algol or Beta Persei. October 10th, it's at minimum at 8:41 p.m. and then it brightens through October 11th at 12:11 a.m. So another one of David's challenges issued here. And then if you're doing the Explore the Universe program, the autumn constellations that you'll have an opportunity to view, Pegasus, Andromeda, Cassiopeia, Perseus, and Aries. So take a look for those. And then of course, the autumn stars. So the ones that are indicated with an N are good for the SynScan Align system for navigation. So you'll have an opportunity, if you're doing Explore the Universe, to explore and observe Mirfak, Hamel, Alpheratz, Algol, Shadar, Markab, and Sharatan. For autumn deep sky objects, here is David's challenge of Melat 20, or Alpha Persei. It's an open star cluster in Perseus. I'll take a look at that. And then for double stars, we have Alpha 1 and Alpha 2 Capricorni. It's a wide binocular optical double. Alpha 2 Cap is a yellow star, and Alpha 1 Cap is a yellow supergiant. So for those doing Explore the Universe looking for double stars and interested in double stars. And that is it. Any questions? A good month. This is my favorite month, so I'm excited.
Yeah, the Perseus cluster is one that I've actually observed over the past week in 2 different locations. It's such a glorious open cluster.
Yeah.
It really is beautiful.
Great. Wishing you clear skies. Hopefully you have better weather than we do today.
I don't think we are. We're under the same cloud here, Lisa, and I think
you guys deserve a break.
Yeah. But thank you. You did a fabulous job on David's behalf, and I appreciate you volunteering to do this on his behalf. Thank you.
My pleasure.
Okay, so I think last but not least is me with news from the board. As you can appreciate, there's never a dull moment with the board. There's always something new that we'd like to bring to your attention. If you have any questions or would like to bring something to the board's attention, please contact me at president@halifax.rasc.ca, at least for the next couple of months, and then you can bug somebody else thereafter. But for now, it's to me. Our Halifax stars. Well, first and foremost is Blair MacDonald, another edition of his Imagers Corner in the October 2022 JRASC, starts on page 195, and he explains LMS, or the layered mask stretch, in it. So for those of you that are in astroimaging, you'll find that of great interest. And in Earth Sky News, Dave Chapman, his photo of Comet C 2022 E3 was highlighted in the top stories for the week of September 17th. Congratulations, David. And of course, Jason Dane. Apparently on the September equinox, Jason was contacted about supplying a picture of the sunrise on September, well, whenever the equinox was, the 20th. And there's his photo in amongst the 24 that are there. So if you're interested, go look for the APO, the Astronomy Picture of the Day, and you'll see Jason's picture there taken at the Eastern Passage. Congratulations, Jason. And that brings me, speaking of photos, to the Halifax Center Photo Contest. Just a reminder to members, you really want to shine like a star? Well, then we need your photos. There are 3 categories in the contest: wide field, solar system, and deep sky prime focus. And plus there's also a People's Choice Award that is given out annually. The submission deadline is Saturday, November 12th, which gives you another 6 weeks. So all those photos that you've been amassing over the summer, now's the time to compile them and submit them to the contest. The winner will be announced at the AGM on December 3rd. And how to enter? Very simply, go to our website, halifax.rasc.ca, and you'll see I've circled the menu item imaging, and that provides all the contest details in terms of the criteria and how to submit your photos. So really looking forward to it. To enter the contest, basically 2 criteria. You have to be a resident of Nova Scotia and be a member of RASC Halifax Centre. So regardless of where you are, that includes you, Lisa Ann, and others like you. Because you're a member, if you have photos you'd like to submit, please do so. And speaking of Lisa Ann, the reminder regarding Nova Notes. What you see here is the cover of the previous edition from May, June. If you haven't read it, please do so. Thank you to Lisa Ann and to John for another fabulous edition. And they're waiting for submissions for our next one. And they've, because of the challenges we've had in this province over the last little while with Fiona and whatnot, the date for submission has been extended to Saturday, October 15. So if you have a book review, photos, an article I'd like to submit, please contact Lisa Ann by going to the Nova Notes editor at halifax.rasc.ca. With governance, there was just a minor little thing done here with respect to the position description for a national council rep. In reviewing something earlier this month, I noted that our qualifications for the national council rep stated may be an elected director on the board or be appointed by the board. Well, that didn't match our bylaw. So now it does match the bylaw, and the qualifications now read, must be an elected director on the RASC Halifax Centre Board of Directors, and in the term limits, they are appointed as the rep for 1 year by the board. So that minor change has been done. It doesn't affect what the person does or anything, just how they're selected. Inclusivity, diversity, and recruitment. What you see here is certainly the statement that I read at the beginning of every meeting, just so that members appreciate the fact that there are no exclusionary clauses within our centre. To that end, we want to extend an open invitation to others to join the RASC Halifax Centre, regardless of whether they're a majority or a minority, any age group, they're new to astronomy, they're experienced in astronomy, or they're a professional. We welcome everyone. We certainly would like to see more members and more diversity within our center being represented, given our increasingly diverse society that we now live in. Beginning in January 2023, there will be a newly elected board of directors. And the board, the current members sitting, have agreed that the new board should and will invite a member from the RASC Inclusivity and Diversity Committee to do a presentation on how we can acquire a more inclusive and diverse membership, and give us some insight as to how we can go forward with this. So in the interim, we'd like members to think about it. How do you think we can and should expand our membership to others in our communities? And we're interested in how you feel about this in terms of how do we go about, what groups should we approach, how do we approach them, etc. In other words, we'd like the membership to get involved in this particular aspect of our center. We'd like to, it's not that we're lacking members, that's not the issue. We do just like to have more members and to have a bit more cross-representation as well. So we need you. Well, why? As you can see from the picture that I posted here, we all come from different threads or different walks of life. And what's interesting is that when we get together, we weave an incredible thing at the other side. So together we can make this wonderful fabric. So keeping in mind that the Halifax Centre is of, for, and by the members. We're all volunteers, regardless of what position we hold, be it on the executive or be it just as a regular member. And our center is what we, the members, make of it. So we'd like you to be part of that team. It's fun and rewarding. Your participant and input are needed, and it allows you to be in the know, gives you a bit more information when you're involved, and certainly gets you to know more about what you're interested in and get to know each other. I've met some amazing people, and I'm sure the members that are sitting here will attest to the fact they also have met incredible folk through their association with the members that we do have. Also, it can be appreciated that as within any volunteer organization, it always seems to be that core group of individuals conducting committees and being involved in events, etc. Well, there comes a point, unfortunately, where some of these folks are getting burned out, and we'd like to mentor other people coming up through as to how they can be involved in these roles. And keep in mind, as it says here, more hands make light work. Learn new skills. I've learned quite a bit about observing, sketching, imaging and image processing, not so much for myself, but others I know have learned quite a bit. Equipment setup and repair, and all sorts of other topics related to astronomy, and mentorship. You can be one, and certainly like myself, when I first started out, I found one. In fact, I found a few. So those are several reasons why you could and should be involved in our center. Also want to bring to your attention that the 2023 nominations for the board are open for all positions. Wouldn't it be interesting if we actually had an election this year? So all positions are open for nominations. The two that are featured in green are certainly ones that the people currently sitting in those positions, myself as president and Greg Dill as treasurer, do have to step down, as we have fulfilled our maximum number of terms that we can sit in those positions before having to step down. So we are looking for those positions in particular. Peter Hurley is our, nominations committee chair, and he would like all nominations in by Saturday, November the 12th, as that is the date when we have to announce all the nominations. So if you'd like to step up or have questions regarding the nominations, please contact Peter at secretary@halifax.rasc.ca. If you're wanting to know what the responsibilities of those positions are, you can go to our website to About Us, and in there are the position descriptions, and you can look up the position description that you are interested in learning more about. So we'd like your participation at meetings, and we're not talking a major presentation, we're talking little short snippets. You have a topic or a book review or equipment review you'd like to give, we'd love to hear it. I'm sure other members would love to hear what you're reading, or especially if you have a piece of equipment that you think is the best thing since sliced bread or maybe burnt toast, we'd like to know. Observing strategies or observing fiascos, good observing sites, those serendipitous observations, the oh wows, the discoveries. Attend, and you can attend in person or virtually, and I'll speak to that in a few moments. Or maybe you'd like to be the MC for a meeting, which means you don't have to know a whole lot about anything except how to introduce the speakers at the meeting. So we'd love to have someone on a regular basis or a one-off be the MC for one of our members' meetings. You can also be involved by joining one of our task teams or subcommittees. There are some that are listed there. It's a team effort. Keep in mind, and I always say it's a team. Everyone is of equal footing, and we support and back each other. And we learn a lot from each other too, because of our various experiences and numbers of years within the organization. And it's fun. I can't say that there's ever been a meeting where it's been dull and boring. So the heads up, our 2022 meetings, well, we've got two left, November 5th and December 3rd, which also happens to be our AGM. And you notice that I have the depiction here of the Zoom, and I said plus in person. Fingers crossed. Both starting November 5th, you will have the opportunity to actually meet in person at SMU, keeping in mind that for now you will be required to wear a mask while in attendance. Or if preferred, you can attend via Zoom, and we'll keep you posted on that. The team is meeting, and hopefully this month getting all the questions and technology stuff squared away. So Zoom and in person, our hybrid meetings are becoming a reality. Special events, as Lisa Ann pointed out tonight, is International Observe the Moon. The board had decided for various reasons that we couldn't organize an event here specifically, but should the clouds clear, please do feel free to informally organize something in your neighborhood at the end of your driveway or whatever, or with family and friends. Do something if you can, skies permitting. The Discovery Center, there is an event, I believe it was also supposed to be held this afternoon, but it's been postponed to October the 15th. And maybe Peter, if he is here now, can mention something. I believe the focus will be on the planets that particular day. Also, I'm sure you can appreciate that Fiona wreaked havoc on our barbecue, so it has a new date has been set. It's Friday, October the 21st at 5:30 p.m. and the rain date's the following night. Obviously, it gets darker sooner, as Lisa Ann also pointed out. So we will have it won't have to wait as long before it gets dark and members can actually enjoy the observing night. Information about this is on our website. So if you'd like to read more about the barbecue, it's there. And with respect to the RASC calendar order, if you read the news from RASC today that came out, you will know that the calendar is now available online for purchase. As I mentioned last month, the center is not purchasing calendars for sale because in years past, we had done that in-person meetings and sold them there. And yes, I do realize we've got 2 meetings coming up, but we made the decision not to make a bulk order. So members are asked to purchase their own online, and you can do that. Just follow the links that are in the newsletter that just came out by email today, or you can go online to the e-store and purchase it there. And last but not least, I'd like, on behalf of the RASC Halifax Center, I'd like to extend our condolences to the friends and family of Wendy Levy, who passed away this past week. So to those who knew David, on behalf of our center, we extend our condolences to him and to all the family and friends that are here. I never got a chance to meet this dear soul, but I've heard great things about her, and certainly her astronomy work is very well known. So, any questions? All right. Well, that's October 1st, folks. We've got a lot coming on in the coming month, and next month, our next meeting is November the 5th. So same time, same station, and we look forward to all the presentations in the coming month. I'm going to stop recording, and those that are wanting to stay on for the chat, please do so. Take care, everyone. Remember, starting at your feet, look up. The sky is open most nights.